What if I told you that the most popular way to generate IDs, UUIDv4, could be silently wiping out half of your app's speed? In the next 10 minutes, we'll uncover the hidden disaster lurking in your database tables. Hold on. Most of the tech world treats UUIDv4 like a silver bullet. But what if the bullet is actually a wrecking ball? Let's flip the script and see why the unique part is the least unique thing about it. You've been there. You add a UUIDv4 column. The migrations run. And everything works. Until the query planner starts choking. Indexes balloon. And your latency spikes at the worst possible moment. Your team's sprint burns out. Tickets pile up. And the product roadmap gets delayed. All because of a 128-bit identifier that looks innocent on paper. What if you could keep the global uniqueness you love, but ditch the performance nightmare? In a moment I'll reveal a drop-in replacement that slashes index size by up to 70% and restores query speed, used by the likes of Google and Netflix. Stay tuned. First, let's dive into the anatomy of UUIDv4. It's 122 random bits, which means each insert lands anywhere in the B tree. The result? Massive page splits, random I/O, and bloated indexes. Contrast that with UUID, a lexicographically sortable, time-based identifier. Because the prefix is monotonic, inserts always hit the tail of the index, preserving locality and keeping pages warm. That alone can cut index fragmentation in half. Now, let's see it in action at scale. Netflix migrated its recommendation logs from UUIDv4 to Snowflake IDs. Twitter's 64-bit, time-ordered IDs. The move shaved 45% off read latency and saved terabytes of storage on their Cassandra clusters. Amazon's DynamoDB also recommends using monotonic keys for hot partition avoidance. The pattern is clear. Ordered IDs equals happier ops. Common mistake number 1. Copy-pasting a UUID generator and assuming it's production ready. Mistake number 2. Adding a UUID column as primary key after data is already loaded, causing massive table rebuilds. Mistake number 3. Forgetting to set proper clustering on time series tables, which leads to hotspot partitions. Each of these blunders can cost you hours of downtime and thousands of dollars in cloud spend. Here's a battle-tested migration recipe. First, add a new UUID column with a default generator, e.g., $UUID_generate, in Postgres. Next, backfill existing rows in batches to avoid lock contention. Then, create a unique index on the UUID column and gradually switch foreign keys to reference it. Finally, drop the old UUID column once you've verified the new primary key is stable. Run explain analyze before and after to see the index size drop from 12 GB to 3.5 GB. After the migration, you'll see concrete wins. Query latency improves by 60 to 70%. Storage costs shrink dramatically. And your replication lag disappears. Teams report faster C pipelines. And the ops board finally goes quiet. In short, you get a leaner, faster, and cheaper database, without sacrificing global uniqueness. For the real power users, combine the best of both worlds with a hybrid key. Take a 48-bit timestamp, tack on a 16-bit node ID, then finish with a 64-bit random component. This gives you strict ordering, collision resistance across data centers, and the ability to shard by node ID. It's the technique behind Google's Spanner GUIDs and is rarely discussed outside internal talks. If you found this deep dive useful, smash that subscribe button, join our Discord for live migrations, and hit the bell so you don't miss our next episode on the hidden costs of worms in 2025. Stay sharp, code smarter. And see you in the next video.